where were we? Well, we were here. We're always here. Yeah. So we're like Fourier series of odd and even functions. So remember, we introduced this terminology for two types of functions. These are functions with special behavior, very nice behavior. The function f is even. This means that f of x is equal to f of minus x for all x. That's an even function. So they take the same value either side of the y-axis. So an odd function is not where they take the same value, but they take values of equal magnitude but opposite sign. The same argument, the same magnitude of argument either side of the y-axis. So in algebraic terms, that's f of x is equal to minus f of minus x. Okay, so this is the definition of two special types of functions. And last time, okay, we investigated this a little bit. A particular note, in particular, the basis function cosine nx is even for all n bigger than or equal to 1. And the other type of basis function in Fourier series, the sine function, is an odd function. It's what we saw last week. And then we proved last week the theorem about how odd and even functions behave under multiplication of functions. And it's nothing too earth-shattering. It's just really tracking through the consequences of the fact that a negative number times a negative number is a positive number, positive times positive is a positive number, and positive times negative is negative. So just tracking through the consequences of that gave us theorem 3.2. Just be a little bit careful with the result because unfortunately we're using the terms even and odd here. Of course, we also use those for divisibility by 2 in the integers, but there's a subtle, it behaves kind of slightly different here when you're talking about products of functions. So for functions, we have that even times even is even. Even times an odd function is odd, but odd times odd. And if this was integers being divisible by 2, we'd know that an odd number times an odd number is an odd number. But if we're talking about functions, odd times odd is an even function. Negative times negative is positive. We discussed that last time. Now, last time we indicated just by talking about the graphs of the functions, we kind of explained theorem 3.3, but I'd just like to go through a proof of that now, how you kind of formally prove this algebraically. And this is what's going to allow us to simplify the treatment of the Fourier series when you're taking the Fourier series of an odd function or of an even function. So the first bit we're going to prove here. So theorem 3.3 relates to taking an odd function or an even function and integrating it across an interval centered on the origin. We're talking about an integral minus t to t. And the theorem says two things. It says if it's an odd function, so h there is an odd function, and the integral of an odd function is 0, integrated across this interval centered on the origin. And if it's an even function, so that's the g there in that statement. When you integrate the even function g, if you want to, you can re-express that integral as just twice times the integral over the positive part of the integral. So we argued for this by kind of pointing out features, sketches of typical graphs. Typical odd or even functions, but that's maybe not that satisfying or that persuasive. Although in this case, well, it didn't any reason, but we can prove it formally using exact expressions and using known properties of integration. So we'll prove it formally. First of all, any questions just about the definitions, about those properties of right. So let's take the odd case first. So we'll let h be an odd function. Now it will help to say that, to declare that we're taking that as an assumption, we may as well spell out exactly what that means, i.e. for all x, every real number x, h of minus x is minus h. The two values take opposite sign. Quoted it slightly different. Yeah, I quoted it. Well, this is quoting, it's the same definition, just the minus sign. So, the two values take opposite sign. So if we consider this kind of integral, integrating from minus t to t of h of x dx, say, well, what can we do? So ultimately I want to show that this is 0. Sorry, hang on. So I need to work my way to 0. So at the point when we discussed it last week, because it's taking values of opposite sign, means whatever kind of contribution to the integral you get on the right-hand side of the domain to the right of the y-axis, you get the negative of that contribution from the behavior of the function to the left. So really, we just want to make that argument formal and exact. So in order to do that, we should split up this integral into the sum of the two subintegrals. So that's the first case where we're kind of using a known property of integration to allow us to do it. So any integral along an interval, you can split that up to first integrating along the bit of the interval and then integrating along the rest. Choose any intermediate point you want. Of particular interest here is the intermediate point 0. Okay, and this is going to be the way I'm going to show that this whole thing is equal to 0. So I'm going to make one of these look like the minus of the other. So I'll leave one of them alone. I think I'll leave the second one alone. Yes, I'm going to leave this second one here unchanged and make the first integral explicitly make it be the negative of this 2. Cancel out. So just put that comment in here to explain what I'm going to do. We will make re-express the first integral as the negative of the second. can I turn this first integral into a comparable thing to compare to the second integral? Well, the second integral takes place over x values between 0 and t. This one takes place over x values between minus t and 0. So first of all, I'll make them take place, I'll make them both be integrals over the same set of x values. Okay. So I'll use a substitution. Well, instead of x, we'll use new variable t, which will be the negative x. So in this first integral, as x varies from minus t to 0, t will vary from plus t down. We'll go through the same set of numbers that second. So we're using integration by substitution. So the relationship between the differentials then is, of course, dt is minus dx. And we'll have to change the sign of the limits of integration as well. So the integral minus t to t. I could just continue to change equations, but text in between, so I'll rewrite the left-hand side. So instead of this first integral, I'm thinking of the integral from t 0 of h of, now what is this? This is h of x here, so this should be h of minus t. And instead of dx, it's minus dt. I'll leave the second integral. So this looks good now, because now this first integral is happening over the same values that the second. Of course, this function h could just be any old function at the moment. I haven't used the fact that it's an odd function. So but it's easy to see how to use that. The fact that h is an odd function suggests that I should rewrite h of minus t negative h of t. Negative h of t still equals minus t. That was integration by substitution. Justification for that is since h is odd. Well, these two minus signs are going to cancel out. They're both multiply together, so it's a positive sign. And then the two integrals are nearly looking the same, except this one integrates, the second one integrates from 0 up to t. First one integrates from t back down to 0. So another key property is the fact that we change the direction of integration along the interval. What happens when you change the direction of integration? Change the sign. You're running in the opposite direction. So whatever value this integral has, when you go along it through it opposite direction, going to pick up a minus. So in total there's 3 minus signs. So in total I've got minus h of t, and then this is 0 to t. The fact that this second integral is quoted in terms of lexes, there it's just a label for the variable of the function. This one is quoted in terms of t. Ours is the label for the variable. The two integrals are exactly the same, except this one is minus. So obviously they cancel. So that what we did finally there was just changing the direction. Then it's just the observation of the two integrals are the same. formally, and it's really just a formalization of correct argument. Last time, we were just kind of pointing at a wibbly wobbly line of a typical function, which I reflected so that it was doing the negative of its behavior. The other half of the plane was again positive areas again to the right, cancel out the negative areas to the left, vice versa. Well, this is just doing that formally by making this substitution first. So that proves that half of this. The integral of any odd function through an integral centered on the origins. Similarly, we won't do it in such fine detail. Secondly, if we let g be an even function, i.e. for all x, g of minus x is the same as g of x. They don't carry opposite signs, they use the same value. Well, we can redo the same splitting up as we did before. The integral minus t to t, g of x dx. Using the same substitution, we go to integral t to 0, g of t minus dt, g minus t. So just exactly the same thing we had before. G of minus t times minus dt. The second one 0 to t, g of x dx. But now you see the fact that g is even means this just changes to g of t. You still got this minus sign here, so we get to the front now. So that's dt. And now we can flip the direction as well, which introduces another minus sign. We only get two minus signs. But before we got three, because the h of minus t gave us minus h of t. This time, because we're dealing with an even function, g of minus t just gives us g of t. This minus sign on the dt is right here. Then we flip it, so it's t. That's dx. We now just have the same integral twice. There's no longer minus sign. So let's see, it's twice times the integral from 0 to t. Again, don't be thrown by the fact that they're quoted using little t. X, the only variable integration. All it's doing is simplifying the argument. Again, it's just formalization of the graphical visual argument. So this now gives us a pretty good understanding of the functions and how they behave. So in theorems 3.4 and 3.5, just draw out the consequences of this for even and odd functions. Because, remember, our basis functions, cosine and sine, well, all the cosines are even functions, and the sines are odd functions. So, for instance, in theorem 3.4, it's not really a complicated proof, it's just pointing out how all the other properties combine. For an even function, g is even, then the combination, the product, g of x times sine of nx this is, well, it's even times odd, so it's going to be odd. It's odd for all n. So that means the Fourier coefficient Bn Fourier coefficient, because this is the integral of this odd function, nx dx, this has to be 0. So there aren't any sine functions in the Fourier series for this function. Okay? They're all just multiplied by 0. So nice one there. And also the product g of x times cosine of nx, even for all n bigger than or equal to 1. So if you wish to, you could re-express the formula for the Fourier coefficient an as 2 over pi times the integral from 0 to pi of g of x times that's the description. It had to be a b because it's equal to the integral minus by g of x sine. Okay, so it's just, these are just putting together all those properties. G is even and sine is odd, then g times sine is odd. So its integral around 0 is going to be 0. And if you want, you can re-express the integral of the even function, g of x cosine of x. Both of them are even, so the product is even. Push replace an twice the integral plus. Theorem 3.5 just says the same thing, except for in terms of h, for h being odd. It says the related thing is the same. If h is odd, then product h of x cosine of nx is again odd, but h of x sine nx is even. It's 2 odd functions. And the product of 2 odd functions is an even function. So this implies that the an's, which are integrals minus pi to pi of hx cosine of nx, these have to be 0. So you're integrating an odd function around 0, and if you wish, bn's equals 2 over pi. 2 over pi times the integral from 0 to pi of h of x sine nx. I mean, this can still be 0, but it's 0, but it isn't definite. So it kind of cuts the work in half. You know the function is odd, or you know it's even. Straight away, you know that half the Fourier coefficients are definitely 0. Lots of the other ones are 2, but you get a result for free. Well, not for free, you have to prove it. It's in the blanks. Any questions? We'll do an example now. Even function, I think. We're going to take the function x squared and derive its Fourier series. I think we'll get another one of these interesting register. No, the printer wasn't working. You guys love your registers. Right. I'll try and get one for the second class. Example. Let's look at f of x equal to x squared. So it looks something like this. Now, is that an odd or an even function? Even. Because it's doing exactly the same thing either side of the y-axis. Positive arguments and negative. Clearly f is even. If you really want more proof, you just consider what f of minus x is. Of course, it's minus x all squared, which is x squared, which is exactly what f of x is. So there you have it, f of minus x. So therefore, we know that previous theorem, what was it, 3.4. Theorem 3.4, we know its Fourier series is of the form f of x, x squared, well, it's a half of a naught, some kind of constant term, plus a load of these cosine functions. The sine functions aren't there because well, they are there, but they're all multiplied by 2. And its particular Fourier series is given there in the question, so we'd like to confirm that. So it just takes a few integrals to confirm that. Very often a naught is treated separately, so this will be 2 over pi times the integral from 0 to pi of the function f of x dx. This is 2 over pi equals 0 to pi of x squared dx. Easy. X cubed over 3 evaluates at 0 with pi. So what is that? 2/3 pi squared. 2/3 of pi squared for a naught. So the constant coefficient you kind of do on its own because it doesn't feature cosine function. Usually then all the other ANs can handle together. Just do the integral parametrically parameter n. So maybe, hopefully we can do all these n's together. AN is 2 over pi. If we're using this alternative formula, so we just integrate it from 0 to pi. And f of x cosine. So this is 2 over pi, which goes 0 to pi of x squared cosine x dx. Now you see you have to integrate x squared cosine x, so and then you think it's okay because you realize that's just integration by parts. So after the x squared has been differentiated a couple of times, it go away, just left with this is 2 over pi at the front. So this would be, you have to write the cosine as a derivative. So that's sine nx x over n. That is to be evaluated at 0 pi. And then you're subtracting the integral from 0 to pi. Differentiate the factor 2x times sine nx over n. Yes, integration by parts once. Now, but that first evaluation, this well, you see the sine is evaluated at integer multiple of pi, 0 or pi itself. So that's all 0. 0, so it's essentially this down here. So there's a 2 there which can come out. It's got a minus sign. So it's minus 4 over pi. X. Bring the n out as well. Simplify it. So it's x times the sine of nx dx. So that needs another integration by parts. Minus 4 over n pi. Yeah, so it's x times what is it? Minus cosine nx over n. That's going to be evaluated at 0 pi. Plus integral 0 to pi cosine nx. So we're nearly there. We've got the minus 4 over n pi. So you really need to be able to graph through these integrals quite confidently. So you're evaluating this first one at pi and 0. Well, you evaluate it at pi, you're going to get minus pi times the cosine of n pi. There's another n there, whatever that is. Of course, you don't get the thing when you evaluate it at 0 because you've got an x. So you evaluate that at x equals 0. This integral here, well, cosine, whatever it is going to integrate to sine nx, another n. But look, you're only going to evaluate that at 0. Sine of some integer multiple of pi, sine of 0, that's all you can do. So you don't get any contribution. So it seems to simplify somewhat. Remember, this is an. An is simplified. These pi's cancel. So it's minus 4 over n squared cosine n pi. Sorry, minus. Cosine n pi is pretty easy to understand. Cosine times an integer multiple of pi is either going to be plus or minus 1, depending on whether the integer n is so this is going to be minus 1 to the power n times 4 over n squared. So it's plus 4 over n squared when n is even, or minus 4 over n squared when n is odd. So that's our second. Well, that's all the other Fourier coefficients, and that holds for every n bigger than or equal to 1. So this confirms the Fourier series as x squared. So it's a half of a naught. Well, the a naught, you look at it, was 2/3 of pi squared, so it's going to be 1/3 pi squared. Then you're going to have a sum from n equals 1 to infinity of minus 1 to the power n 4 over n squared times cosine nx my an, my coefficient an times cosine of x. There's a couple of things can be brought outside. The 4 can be brought outside. Simplify it. It's kind of worked. Yeah. So you see how the fact that we were able to exploit the fact that this is an even function to get at the Fourier series. You could have gone and tried to evaluate what Bn was, done the integration by parts outside, just get where all the individual bits be 0 or whatever non-zero bits you got cancel out each other. Now, again, we have an interesting thing we can observe here, is the fact that we've got an infinite series representation for this function, but we've got pi. So, what if we evaluate this at 0? Now, this function is completely continuous in the interval. So, at x equals 0, there's none of this iffy business of this being a point of discontinuity where the Fourier series actually gives you the halfway between the left and right hand limits. It's just a normal, the function is continuous here. So, the two sides of the Fourier series are exactly equal. So we can evaluate it at x equals 0, and what do we get on the left-hand side? We get 0 squared. But on the right-hand side, you get a third of pi squared plus the sum from n equals 1 to infinity minus 1 to the power n 4 over n squared times the cosine of n times 0. Cosine of 0 is 1. So you just get this. So that means 0 is a third of pi squared plus, take that 4 out. Just start looking at a few of these. This is, what is this? This is 1. Minus 1 plus 1 over, well, I'll write like this, 2 squared minus 1 over 3 squared plus 1 over 4 squared. So it's the words you'd say that's the alternating sum of the squares of all the integers. And just a little bit of rewriting, you can get pi squared over 12, so just divide across by 4. Just get pi squared over the other side. So you see what this is. Nice series for pi, which is different to the one we derived last time. I'll put up the visualizer pages from last time. Must have neglected to post the visualizer pages from last time. Sure, I did. Last time we showed looking at a different Fourier series, and we were able to show that pi was 4 times this was the alternating sum of all the odd integers. So this was 1 minus a third plus a fifth minus 1/7 plus 1/9. Get this, like, it's really surprising for the series one. Alternating sum of all the squares of all the integers, or well, that's related to the square of pi itself related to the alternating sum of all the integers of pi. Nice. Okay. That there for now. So when I'll see you in an hour, do some more examples. There's another section there. You see half-range series. So have a look at that. Okay, so I'll see you after the order.